InterPlanetary Consensus IPC Data Economy Hackathon. So today we have our team already. Before we start, let me give you the background of this hackathon. For DoraHacks, the biggest developer incentive platform, it's an honor to support the Filecoin ecosystem and this hackathon. And we're looking forward to all the incredible projects building at this hackathon. So today we have Matt Hamilton. He's developer advocate at Protocol Labs, and he's doing a workshop about how to run your dApp across interplanetary consensus subnets using general message passing. So without further ado, let's welcome Matt to start. And we have also other workshops, so feel free to also subscribe to our YouTube and Binance Live. So once you're ready, please start.
Fantastic. Thank you very much, Jan. So yes, welcome to this workshop. So my name is Matt Hamilton, and this is a talk about running your dApp across subnets on IPC, Interplanetary Consensus System. So what I'm going to do in this talk is I'm going to do a very quick recap about what IPC is and a little bit about its architecture. We're going to talk more specifically about general message passing, GMP, and link you to an example of using that for, in this case, an ERC20 token and how you could move that between subnets. So, like I said, I'm going to go through a little bit of background just to get everybody up on the same page. If you haven't been on any of the other workshops, as Jan said, this is the 10th workshop of this series. And I'm just pointing out here a couple of previous workshops in this series that will give you a bit more background information on what I'm doing now. So if you're watching this as a recording and any of the bits that I cover as part of this intro, you want some more information on, go back to here, and there's two talks I'll call out in particular. A talk I did as part of the kickoff sessions that we had. And so that talks about IPC in general and the bigger picture about IPC. So you can go there, there's a QR code, and it's on DoraHacks' YouTube. And then there's also a talk by my colleague, Sarah Tiem, who did a talk about deploying your first custom subnet on IPC. And again, there's a QR code there that will take you to that. Because everything we're building here, we're building on individual subnets. So that's kind of the first step that you'll need to do as part of whatever project you're doing, is deploying your own subnet. And Sarah covers that there as well. And there's also, just to highlight, docs.ipc.space. So that's on a documentation site. And there's some information in here, like, for example, a quick start on deploying a subnet as well to get you going. And this site is being continually updated. There'll be a lot that's happening over the next week being put in here. So do come back and check. If something you're looking for is not there, then come and have a look here, and you should see it here. Okay. So what is IPC? So IPC is a scalability technology developed by Protocol Labs, the people behind Filecoin and IPFS, libp2p, and it allows unlocking planetary level performance for Web3, right? So the idea being is that at the moment, a lot of very high volume applications in Web2 are not really possible in Web3 just because of the limitations of trying to maintain consensus on a decentralized network in most cases. So the idea that IPC does is it takes up and it breaks the network up into subnets, and those subnets could even be regional or application specific. So it's infinitely scalable because you can create subnets upon subnets upon subnets. So you might be familiar with layer 2 subnets such as Polygon or Arbitrum off of Ethereum. And with Filecoin's a layer 1 network, you can then create your own layer 2 off of it, or layer 3 or layer 4, layer 5. So you can chain them off of each other recursively. It's deeply customizable. It uses the Filecoin virtual machine. Filecoin virtual machine is a polyglot VM, and there's a EVM layer on top of that. So that's what most of you will probably be interacting with if you're used to Solidity. You'll be using the Filecoin Ethereum virtual machine and your standard tools that you might use for that. So Hardhat, Forge, Remix, that kind of thing, right? So, but having your own subnet means you can customize it. So you can choose your own gas schedule, native tokens, membership rules. So it might be a private subnet, it might be a public one. You can, choose all of those parameters specific to the application that you want to run on your subnet. And it's modular. Like I said, it's built on FVM. You can deploy, for example, your own custom built-in smart contracts, what are called custom built-in actors and syscalls. So there's a previous talk I did a few days ago. Again, it'll be on the DoraHacks channel about creating your own custom subnets, custom syscalls and built-in actors. And in that example, there's a syscall that goes outside of the EVM sandbox, and in this simple example, reads the number of files on the root file system. But you could do it. You could use it for applications that go beyond what you're allowed in EVM. So, for example, you might have tried doing something like parsing JSON or parsing any text within Solidity is very difficult, right? There aren't text processing commands within Solidity, functions within Solidity. So you could do something like create a JSON parser, access via syscall, via custom actor, and then from Solidity within there, for example. So I mentioned with IPC that it's hierarchical, it's recursive, you can create subnets off of subnets. Now we're mainly doing this off of Filecoin because that's the main network that this is kind of coming from. But you can actually deploy it to any other EVM network at the moment as well. So you could actually deploy it to something like Ethereum directly. And there's people that are looking at doing it with non-EVM networks, such as Bitcoin, for example. So you could scale horizontally based upon applications. So you might have one subnet to do with game, subnet to do with databases, for example, subnet to do with machine learning, or you could scale it vertically based upon geographic region, right? The laws of physics means it takes a certain amount of time to propagate a signal from one side of the planet to the other. So you might have one subnet that is just within the confines of a data center because you want millisecond response time, but that can then connect up to other subnets in other geographic regions, for example. So I mentioned here about the kinds of things that subnets can host. So really, it is imagination as part of this hackathon. What would you use a subnet for? You kind of have your own subnet, you can customize it. So what kind of things would you want to do with? So we're going to be talking about general message passing. So really we need to look at a little bit about the architecture of how IPC works. Now there's a couple of actors, a couple of smart contracts on there, one called the subnet actor and one called the gateway actor. And for each network, there's one gateway actor, and then there's a multiple subnet actors, one for each subnet that is connected onto that network. And they are manipulated by a tool called IPC CLI. So again, if you go back to one of the previous talks, and I'll bring the links to those up again later on, you can see how you can use IPC CLI to spawn your own subnet and interact with that subnet. So we have these two main actors, a gateway actor and a subnet actor. The gateway actor acts, in this case, one of the most important things it does for GMP is it's a mailbox for cross-net messages. So you would send a message and it would go from the gateway actor on your network up to the subnet actor of the parent through to the gateway there as well. Now, at the moment with GMP, you can only do single hop. So you can only go from a parent to a child or a child to a parent. You can't go between siblings at the moment. So that is a future feature that we are intending to release, but it's not there at the moment yet. So you can't go in this example between these two subnets, T01 and T12. You can only go between the root and the subnet. So again, like I said, there's two previous talks I encourage you to have a look at that talk a bit more about the general, expand on more detail about the general kind of concept of IPC and what it enables, and also the walkthrough from Sarah TM on how to actually deploy your first subnet. So what we're going to be doing is we're going to be looking at an example of a ERC20 contract. Now, this is currently on a branch by my colleague Mike. There's a QR code there you can scan. The URL is also on this slide here as well. Now, eventually, hopefully this can be merged into the main branch. So if you're looking for this and this URL changes, then it will be within the main branch of the network. But you should be able to look there in the directory called extras. In there, in the root, you'll see extras, and within there, linked token. So that's where that will be. But for the moment, it's on a branch, but it will be merged in, and it may be merged in by the time you watch this, if you watch this a replay. So let's look at the kind of the architecture and the flow for an ERC20 example. So let's say we create a example token. We're going to call this USDC test. It's an ERC20 standard ERC20 token on the network. Now, what we want to do is we want to be able to bridge that token from the parent network down to the subnet, right? So in this case, the parent network is the Filecoin testnet called calibration, and we want to bridge it to a custom subnet that we created. So if you look at this in a wider picture, if you deploy this onto the production, onto Filecoin mainnet, on Filecoin mainnet, there are ERC20 tokens issued by various bridge networks. So for example, Axelair. So Axelair have a USDC token on there. There's also things like Wrapped Fill, for example, on there as well. So if you wanted to use those tokens within your subnet, then this is the pattern you would go through to move it onto subnet. So what have we got here? We've got the ERC20 contract, and we have on here two contracts, one on the parent network and one on the subnet, that control moving the token from one to another. So there's a function on this token, on this contract called lock and transfer. And so you transfer some ERC20 tokens to this contract that then locks those tokens up, and it makes a IPC call to a kind of analogous contract on pardon me, on the subnet. So this what's called replica contract. So we've got the controller contract and the replica contract. It sees this and it then issues a mint command to mint an amount of this USD replica token, right? So on the parent network, the token is locked up. It could even be burned if you wanted to do that, depending upon your implementation. If you were the person that was actually issuing the token on the parent network, you could burn it as well. And then once it is minted on the subnet, you can then use that on the child subnet. Okay. There's then the opposite workflow to go back again, in which if you want to withdraw from the subnet, so there's this burn and transfer method. So remember those replica tokens were minted on the subnet. They are now burnt because they no longer need to exist. This replica contract makes a call to the parent network that then releases the tokens that it had locked up and calls safe transfer to move those back to the origin, right? So that's the reverse flow of what we've just shown. So let's look at the actual code for this. So I mentioned here that we have within GitHub, within the extras directory. So within IPC, there's a folder called extras, and within there, linked token, and there's a bunch of contract source. So within linked token, there is a makefile, and in here are a number of targets to actually automate and deploy this test. Now, the full instructions for this will be on the IPC docs page probably later on today, or definitely this week. But you can call make help, and it will give you the instructions here of what to do. You need to deploy the USDC test token. You need to deploy the replica and the controller. You need to initialize them. And you can then do an approve a deposit, and you can actually check this moving, right? But let's look at the source code of the contracts, because this will give you a bit more information here. Now, again, a lot of this is very bleeding edge and under development at the moment, so definitely there be dragons. But if we look at linked token.sol, well, okay, actually, first of all, let's look. We've got the controller and the replica. Both the controller and the replica contracts are very short, and they actually subclass the linked token contract, right? So let's look at linked token on here. And this implements most of the actual functionality here. Now, it uses some functions from an IPC SDK that we have. So we've got this IPC SDK here. Like I said, that is not fully documented yet, but it gives you the functions, things like IPC exchange, to actually make calls between subnets. And there's a number of data structures here needed as well. So linked token is IPC exchange, so subclass is that. We define a number of variables here from those structs that we imported at the start. So things like the envelope. So the envelope is what is actually transmitted between the subnets. And so it contains things like the method that you want to call and any payment information as well for calling that. Because remember, if the controller is making a call to the replica, there's going to need to be some payment information submitted with that as well. So there's a number of events that are emitted as things go on. So whether the token's been initialized, token's been sent, token's received. But here we go, constructor. So with a constructor, we pass in the gateway address. That's the address of the gateway actor. As I said, the gateway actor acts as a mailbox, so it needs to be passed in as well. And the underlying token. So that's, in this case, this USDC test token. We can actually see, if I just jump back here, USDC test.sol, you can see that this is just a standard ERC20 token here, okay, taken from OpenZeppelin. So going in here, again, linked token, let's go through here. So here's a function here, this lock and transfer. So this lock and transfer actually calls this link transfer method here. So if we go down to link transfer, we'll see where this actually executes the execute path here. Just trying to find it here. Link transfer, okay, yeah, it calls this internal link transfer here. So it validates that the contracts have been initialized, validates that the parameters are acceptable, the recipient and the amount are acceptable. Here's where it captures the tokens. So, now this capture token method is overridden in the controller and the replica contract. So if I just bring those two back up here, let me just bring those up in separate tabs. Controller, replica. There we go. If we look at the controller, you will see that that capture tokens has been overridden. And in this case, it just does a safe transfer from the sender to this contract. So basically, it moves the tokens into this contract to hold them, right? And so it holds those tokens. So that's a capture token. Like I said, you could do a burn instead of a lock, depending upon the actual implementation that you're doing. And that is what actually the replica does. So when the replica captures the tokens, it actually burns them. Because remember, those are the tokens that it minted initially when it does the release tokens, right? So it's in control of those tokens on the subnet, so it can mint and burn them. So capture the tokens. Here's where we now actually call the method on the other side, right? So we package up a message here. We tell it what we want to actually call. We want to call receive linked on the other side. And the parameters are the recipient and the amount. We get the destination address. And we actually perform the IPC call here, right, to the destination which is the contract on the subnet and the message. Yeah. And we record that this transfer has been unconfirmed. So it's actually a confirmation process that once the child subnet has received it and executed, it then confirms that has actually happened there. So that's kind of the process that happens on the parent side here. And like I said, the parent side, it has concrete implementations for capture tokens, at which it does a safe transfer to itself, and release tokens, at which it does a safe transfer back to the origin. So that's how the two of those work. Hopefully that gives you a bit of example to go and have a play around with. Like I said, it's in this current bunch called Mike RS subnet test, multi-subnet test, and that's linked to by that QR code that's here. So that'll take you directly there. If in the future, watching this recording, you do this 404, it probably means that that branch has been merged into main. So go to main, go into extras and go to link token, and you will find it there. Okay. So hopefully that gives you enough information to start playing around. So like I said, just as a recap, within IPC, you have a contract on the parent network and a contract on the child network. You interact with that parent contract. That then makes an IPC call to the child network to then do something. And you can go the opposite direction as well. So you could have a subnet, a smart contract on subnet that actually calls a parent contract that calls someone, for example, the built-in Filecoin actor. So things like the market actor to look at a storage deal. If you're doing something with storage, for example, on the Filecoin network. So there we go. I really look forward to seeing what you build. This timeline is slightly out of date. Open ceremony's already happened. Workshops just been going on. Submission deadline 31st of March, and the winners are announced on the 7th of April. And there's a QR code there that'll take you through to, we've got a Discord and a Telegram group as well. And just a quick plug, if any of you are at ETH Denver at the moment, we have a big presence here and a lot of events. So ethdenver.ipc.space, or if you follow, there's a Twitter account, IPC Devs, as well on Twitter. If you follow that, you'll have all the information there. But we have a whole series of events that are happening over the next week or two in Denver. So we'll be at a number of different events. So Biddle Week, there's the AGI Summit, there's Filecoin Dev Summit, there's AppChain Day, Deepin Day, AGDAO. There's a whole series of events we're going to be at, Pragma, and ETH Denver itself. So if you're around, come along and find us. So thank you very much. I think that's it. Time-wise, yes, great. So 5 minutes, I think. If there's any questions, I'm not sure if we've got many people live.
All right, so thanks a lot for the great presentation. Let's give the audience some time to digest all the information. They've learned a lot about different subnets, general message passing. Maybe you could share a bit more what you would want to see in terms of general message passing. Like there's some applications around it, but like what would be some impactful application you would like to see developers are building?
Yeah, so if you were able to combine it with some of the other sort of features we mentioned, so things like custom syscalls and actors, then you can actually build up something quite interesting that you could have a subnet that has some functionality that is not available on the mainnet or calibration testnet, but is accessible via GMP, right? So I gave the example of, for example, something like a JSON parser, right? Or maybe you do something like some ML inference. Now, that's not something you'd want to do on chain, but you could access via a custom syscall within FEM. Now, if you're doing a custom syscall and a built-in actor, you would need to do that on a subnet because you control that subnet. You couldn't do it on the main calibration testnet because you would need to get the agreement and consensus of all of the nodes on that testnet to actually implement that functionality. But what you could do is you could implement it on a subnet, and then you could access that via GMP from calibration net, right? So if you put all these bits and pieces together, then you could create a subnet that has some functionality that's very bespoke and not possible with general EVMs. And then you could access that via a EVM smart contract, a Solidity smart contract on the main calibration testnet via GMP. So that'd be really cool. So again, something like a JSON parser would be pretty cool because I've hit that a few times, doing something like some ML inference or accessing something maybe like some kind of like Oracle randomness function, some sort of randomness function based upon something that you don't have direct access to on the blockchain could be pretty interesting as well. Maybe like a hardware random generator, or even dev random, just as an example, just as a dummy example. That would be that'd be pretty cool.
That sounds very good. So I don't see any other questions. In the chat is a Telegram group link. So if you are still looking for team members, if you have some questions, feel free to enter the Telegram group and then get support there for the hackathon.
Yeah.
I guess we could wrap it up already. So thanks a lot for the great presentation. The audience learned a lot about general message passing, IPC, and also subnets. And we're looking forward to seeing all the incredible projects building at this hackathon. So you have a bit more than a month till the submission deadline. So if you still have any questions, feel free to join the Telegram and ask for any type of support. And then we do have different other videos coming up, such as the closing ceremony, the demo session. So feel free to also subscribe to our YouTube and Binance. And once again, Matt, thanks a lot for having us today. And do you have any final remarks?
No, just thanks a lot, Jan, and thanks to the DoraHacks team for organizing this all together. And to all the hackers, good luck, have fun, learn stuff, and I really look forward to seeing what you build. And reach out if you need help on Telegram. Thanks.
Thanks a lot. Bye-bye.